Okay, so to put all this stuff about different reference frames on a somewhat firmer footing, okay, I want to introduce the concept of a metric. Okay, so the metric is basically how you measure distance between 2 points in a mathematical space. Okay, um, so the easiest way to do this is give an example. In our normal Euclidean three-dimensional space, okay, the metric is this. Okay, the distance between 2 points squared is the sum of the square of the x separation between them, the y separation, and the z separation, or the squares of you know what I mean. Basically, the Pythagorean theorem. Okay, here's a little excuse me. Here's a little example. Um, and the thing about this is s does not depend on your coordinates. So imagine to put this into sharp relief. Imagine you're holding one end of a meter stick. Okay, and you're holding the one end of the meter stick down here at the origin. Okay, and you can turn the meter stick into various orientations as long as you keep one end at the origin. Okay, and the far end of the meter stick will have different x, y, and z coordinates. Okay, depending on where you put it. But no matter where you put it, x squared plus y squared plus z squared will always add up to 1 meter squared, right? The distance s will be the same even if the x, y, and z coordinates change. And if you imagine taking different axes, okay, without moving s, that's the same thing, okay? So you hold your meter stick in one direction and you change your axes, you'll get different x, y, and z values, but the magnitude of the vector with components x, y, z will always be 1 meter. Okay, so the metric is something that's invariant when you do coordinate transformations. Okay, and I think that's what it means. Now, Minkowski, what he did that was brilliant was he came up with the metric for space-time, and the metric for space-time looks like the metric for normal Euclidean space. Okay, you have the x squared, y squared, z squared, but then you take the time term multiply by c. You have to multiply by c to get the units right. Okay, so this has units of length. Square it, just like everything else. And then this is the weird part. There's a negative sign. Okay, but what he said was basically if you take two events in space-time and calculate the what's called the separation between them, the s squared, that will be the same no matter what reference frame you're observing the events in, no matter what the motion of the observer. Okay, and this is just a quote from Minkowski about how basically this establishes the idea of space-time, which is this fusion of space and time. Okay, so here's the Minkowski metric, and again, this is just repeating what I said last time. The quantity s and s squared will be the same regardless of the coordinates used, which means regardless of the motion of the observer. Okay, and it makes many calculations of special relativity much easier. If you go into a class where you learn this stuff, which you may do in college, um, you will find it's most problems that you can be given in special relativity are much easier if you use the metric. I'm going to give you an example. Okay, so we're going to talk about many years in the future. We've got these spacecraft that can travel at significant fractions of the speed of light, and they can go between stars. Okay, so we'll say there's a human colony on Barnard's star, which is 6 light years from Earth. That's where you live, and you get an invitation to a party that's going to happen in 10 years at Barnard's star. Okay, so the first part of the question is you make the trip on a starship that starts immediately from Earth and travels at constant velocity to get there in 10 years. How much time passes for you while you're on the ship? Okay, and then the second part is what happens if you basically travel at the speed of light to Barnard's star, and then you have to wait 4 years for the party to start. How much time passes for you? Okay, so let's do this here. Okay, so let's start by drawing ourselves a little diagram. Okay, let me do this I'll do it in blue, I guess, and I'll do some lines. So we'll say here is time, here is space. Okay, so this is c times t, and this is x. So here is Earth, okay, and Earth is at this location. And then here, I'll try to draw these in a straight line, 6 light years away is where Barnard's star is, okay? And so let's see, 10 years now, this is the party. Okay, P is the party. Okay, that's 10 years away from now. So now is right here. Okay, and we'll say this distance here is 6 light years. Okay, between Earth and Barnard's star. Okay, this is a little messy, I know. Okay, so first we're going to say you take a straight line path. I'll do that in, I don't know, a huge array of colors. So I'll do that in red. Okay, the straight line path, you do that. Okay, so part A. Okay, so in the rest frame, okay, or the Earth's reference, maybe I should, okay, probably bad to say rest reference frame because that implies that there is some true rest reference frame. So let me erase that and go to, now I don't know which pen I had because this is, okay. So we'll say in, oh, that looks kind of nice. Okay, in the Earth reference frame, okay, or the Barnard star reference frame. They're both motionless relative to each other. Okay, what do we have? We have your distance traveled, x equals 6 light years, and the time taken is 10 years. Okay, so the interval now we're going to calculate as s squared equals, so if you recall, this was negative c times t squared plus x squared. And there's also a y squared and a z squared in there, but we're setting the x-axis being the axis leading from Earth to Barnard star, so we don't care about that. Okay, so we go negative, what's c, the speed of light in light years per year? Well, conveniently, the speed of light is 1 light year per year. That's what a light year is, okay? So this is c here, 1 light year per year, times 10 years squared, okay, plus, and then we get 6 light years squared, okay? So s squared equals negative 1 light year per year times 10 years is negative 10 light years squared, okay, plus 6 light years squared, okay? This is going to be negative 100 square light years plus 36 square light years, okay? So what you get is s squared equals negative 64 square light years. Okay, now, what about in the spaceship's reference frame? We want to know how long this trip appears to take for you, okay? So now we have to basically say, in the spaceship's reference frame, in the ship's reference frame, which is your reference frame, because you're riding the ship, okay, x equals 0, right? The ship, how far does the ship travel in its own reference frame? It doesn't, okay? So now what we do is we take s squared equals negative ct quantity squared plus x squared, okay? And we use the fact that the metric is going to be the same in both reference frames. Or sorry, not the metric, excuse me, the separation, the interval s, this s here, is going to be the same in both reference frames. So we go negative 64 light years squared equals negative ct squared, okay, plus, and what's x? 0 squared. So it's pretty easy now to get down to the point where you can say, okay, so what this tells us is that negative 64 light years squared is, and I'm making this, honestly, at this point you can probably see the answer, okay? Negative 1 light year per year times t squared, and the answer you'll get is t equals 8 years, okay? That is the answer to part A. This is weird, okay? For people who wait on Earth and people who are waiting at Barnard's star, it will appear that 10 years passes while you're in transit from one to the other. On board the ship, only 8 years will appear to pass. That means you will only age 8 years. You will only live 8 years of your life. You will only live 8 times 364, or sorry, 8 times 365 24-hour periods, okay? In every way, it will seem to you as though only 8 years has passed. But when you get there, you'll discover that 10 years has passed for everyone else outside, okay? If you were to do a round trip, okay, I don't want to get off the problem here, but if you were to do a round trip, if you're going to Barnard Star and then back, you would discover that your friends, when you got back to Earth, you would discover that your friends on Earth had aged 20 years and you had only aged 16 years. Okay? So, part A, I'm going to write down the answer for part A, is t equals 8 years. Okay, just to have that. And now, I'm going to erase this. And there's probably a better way to erase all this, but I don't know what it is. And I'm already committed to this. Okay, good enough. So now, what happens if we, in part B, okay, so let me make it clear what I did in red was part A, okay. Part B, what I'm going to do is I'm going to go in a straight line at the speed of light to Bernard star, okay, and then I have to wait around 4 years, okay. So how much total time passes for me if I do that? Well, okay, so let's look at this part. So for part B, we have x equals 6 years, and x equals 6. Now I gotta erase. Okay, x equals 6 light years, and t equals 6 years. Okay, we do s squared equals negative c times t squared plus x squared. Okay, and I'm going to cheat a little bit here because x is 6 light years, t is 6 years. When you multiply by c, c is, of course, 1 light year per year. So you'll get 6 years or 6 light years squared here. So s squared is going to come out to be 0. This is all calculated in Earth's frame. Okay, now in the spaceship's frame, okay, in the spaceship frame, s squared equals negative ct quantity squared plus x squared. Okay, now we found before that s squared equals 0, right? We found that up here, and it's got to be the same in both reference frames. So 0 equals negative ct, that's not c, negative ct squared, oh, sorry, put the negative sign in the wrong place there, negative ct squared plus x squared, and x is 0. Okay, what this tells us then is the time that passes on board the spaceship is 0. This is interesting. Okay, if the spaceship were able to travel at the speed of light, time would not pass for it and for anyone on board. Okay, that's an interesting fact about relativity. That's absolutely true. That's one reason you can't travel at the speed of light, because time would stop for you. Okay, so we've got this for the trip, for the travel. Okay, and then we also have t equals 4 years you have to wait for the part A. Okay, and I'll spell it part A. Okay, so the answer for part B is t equals 4 years. Okay, so a couple of interesting facts here. One is that for something moving at the speed of light, time does not pass. Okay, and we saw this. We didn't go into time dilation, but if we had, we would have seen that as your speed approaches the speed of light, time stops passing, or time slows down and eventually stops passing when you reach the speed of light. Okay, what this means is, here's a question: what's the lifespan of a photon? Well, in its own reference frame, its lifespan is 0, because a photon travels at the speed of light. Time never passes for a photon. If a photon ever has to slow down slower than the speed of light, it stops existing. Okay, which I don't think happens. Okay, anyway, the other thing is, you look at the total time to go from Earth to Bernard star, and then to wait for the party on this path, and it's only 4 years. Whereas this path, the red path, it took you a subjective time of 8 years. So the interesting thing here is that the straight line path through space-time is the longest. If you want to get from one event to another, okay, that's what this problem is. The first event is you getting the invitation on Earth. The second event is the party. If you want to get from one event to the other, the straight line path will actually take the longest apparent time to you. Interesting little fact, okay? But it's true. So there's the Barnard star question. Now, what else does this metric stuff mean? Let's see. Let me go back to my slideshow. So here's a space-time diagram, and we're going to look at how various events on this relate to here, okay? Relate to the origin, okay? So the origin is some event, okay? It's where you are right now, okay? So say you emit a flash of light here, where you are right now. These dotted lines represent the travel of the light emitted by the event. And as we saw in the Barnard star problem, the s squared along these paths will be 0, okay, because this is where ct equals x, okay? So in here, this is what's called the future light cone, okay? This is the set of all events that can be influenced by the light you emit. So one of the things we discover that relativity sort of proves for us is that information can't travel faster than the speed of light. Okay, if there's an event out here and you're right here at this event, there's nothing you can do to affect this event. You can't transmit information there. Without information, nobody can do anything. Okay, so if there's an event here you want to influence, tough luck. You have to wait until that position comes into your light cone right here, because that's the soonest you could get information to them at the speed of light. Okay, so this future light cone represents all the events you could affect. And similarly, you can define a past light cone. These are all the events that you can know about when you're here. Okay, if something happens right here, there's no time for the information about that to get to you before this event. Okay, so this could represent, say, I don't know, Barnard star is actually 6 light years away. This could represent Barnard star 3 years ago. We don't know what the deal was at Barnard star 3 years ago. Okay, we won't know until another 3 years passes and it enters our past light cone. Okay, because it takes 6 years for light from Barnard star to get here, and that's the only way we could know about stuff. Okay, so remember all that stuff we did where we changed. Oh, sorry, and then the other category of stuff is what's called elsewhere. Okay, so I haven't really talked about s squared, but in your light cones, your past and future light cones, s squared is less than 0. Okay, that means you are further away on the time axis than you are on the space axes. Okay, the actual paths taken by light have s squared equals 0, and then the third category of events is what's called elsewhere. Okay, this idea of what Barnard star 3 years ago falls into the elsewhere category. We don't know what happened there. Okay, we won't know for another 3 years. And if you remember that white and red paradox, where they could change the order of events for the left ends of the sticks passing and the right ends of the sticks passing. If you're worried that opens the door to time travel paradoxes, where like you could potentially, by changing the order of events, kill one of your grandparents, you can't. Okay, because the left and right ends passing were in the elsewhere category of events. You can move them around by changing your speed and direction. You can sort of shift where things are. You could take an event that's here and move it down to here by changing your velocity, but you can't move something from elsewhere into the past light cone or into the future light cone. And you can't move something from the future light cone into the past light or into the elsewhere, okay? Because of the whole thing about the metric being the same regardless of your velocity. Okay, if an event is in the elsewhere from the event you're at right now, no change in your speed or direction of motion will take it out of elsewhere. Okay, so that's the idea of light cones. Kind of interesting stuff that you can sort of define this cone of events that you can affect. And it's called a cone because if you thought about what it looked like, say we added a y-axis to this, so y-axis going in and out of the page, then the shape would, instead of looking like just this triangle, it would look like a cone with an axis on the time axis. So that's why it's called a light cone. I think that's about all I have to say about that. But the next one, so what we've talked about so far falls entirely under the category of kinematics. Okay, and what I'm going to do now is go on into dynamics, into mass and conservation momentum and stuff like that. So that's the next one.